Good afternoon, and welcome to the Music and Technology Seminar at Carnegie Mellon. Our guest today is Roger Dannenberg, who is known throughout the world as a music and technology innovator and inventor. Score reading, score following and real-time accompaniment, automated composition, Audacity, the digital audio workstation, remote real-time collaboration, accomplished trumpet player and opera composer. Roger Dannenberg has done all of these things and much more. Let's see what he has in store for us today. Please welcome Roger Dannenberg to the Music and Technology Seminar.
All right, thanks. Thanks very much. Let me start sharing some slides here, and we'll get started. Okay, so first of all, I gave a very similar talk to this about 3 years ago to this seminar. So if you were there and you remember it, I apologize for repetition, which is also the title of the slide. So no pun intended. And I did make some changes, and there's been some new developments since then. So anyway, we'll jump in. I think I wanted to start with just a little personal background. Some of you have known me for a long time and know all this, but I think many people don't. So I got started in the kind of electronic and computer music world in high school when I discovered synthesizers like this one in a music store, and I was just totally fascinated by the ability to construct sounds and change parameters of sounds and hear, the adjustments of individual parameters. And I also started learning to program around that time. This is what the computer I learned on looked like, and you might see a CRT, a cathode ray tube, sometimes called a glass terminal, but anyway, text display, and it looks pretty clunky at the time, but that was only for the operator, the people that actually use the computer's punch programs on punch cards. And so, we've come a long way since then. All of this got me interested in building circuits and building synthesizers, and I studied electrical engineering in college. When that was after going through college and grad school, and just sort of thinking that I wasn't going to make a career out of this, it was just like an interest and a hobby, and I read just everything I could get my hands on. But when I finished my PhD, which was in the operating systems area, I felt like I finally had a moment to take a breath and do something fun. And one of the first things I worked on was computer accompaniment, which is getting computers to listen to live performances. And that was pretty successful and resulted in the formation of a company that's now known as Make Music. But accompaniment was kind of the foundation of their product. Much later, around 2000, we started Audacity in my lab with Dominic Mazzoni, who was a grad student at the time. A lot of people know about that. And then, as Ricardo mentioned, I have been writing opera, and there's one fairly long opera. This is an image from a very early 2000, just before COVID struck. We did a performance, really nice performance downtown in Pittsburgh. And since then, I've written a chamber opera with, and both of these are co-written with Jorge Sastre. Also along the way, there were some great influences that I can mention. This is Paul Cooper, a composer at Rice University, that introduced me to 20th century music, really. Aside from pop music, I was, pretty clueless, and it was a real mind opener. In grad school in Cleveland, had the great privilege of meeting and studying a little bit with Art Benaid, who's a physicist who studied musical acoustics. And I think really understanding how musical instruments work from a physics standpoint has influenced a lot of my work and led to a lot of applications in the computer world. And then when I came to Carnegie Mellon, I again had the incredible privilege of studying with Alan Newell and Herb Simon, not as advisors, but as initially in some grad courses that they taught, and then later just knowing them personally and joining the faculty with them. And they were kind of just unbelievable thinkers, and had a lot to do with me doing computer music work at Carnegie Mellon, because they were really open to any kind of scientific exploration. And I think that encouragement has been great for computer science at Carnegie Mellon, and certainly for me. I also studied trumpet with Tony Pasquarelli here at CMU, and that really helped move me to a level that I could start playing professionally, and had a lot of musical opportunities that also inspired a lot of work that I do in the research side. And then finally, Roger Humphreys, the great jazz drummer, is a local Pittsburgher, but of international fame. And I had the privilege of playing in his big band for 5 years, almost every week downtown, which was really grueling to stay up until 2 or 3 in the morning playing in a club, and then come and take my kid to school the next morning at 8:30 a.m. But it was all worth it, and a great education. So today I want to talk about music structure. Where does it come from? And my answer is largely from repetition. And we'll talk about why repetition is hard for machine learning. And I'll talk about the use of repetition for studying structure in music, and we'll get to some conclusions. So oftentimes music is described as organized sound. So what does this really mean? What is organization? And where does it come from? Well, let's take a counterexample. This is not the way music works, I think, which is natural language. So sentences in the English language, for example, have what I call extrinsic structure. I mean, that's clearly organized information, and speech is, in a sense, organized sound. But speech and natural language relies on the fact that words or sounds or letters have extrinsic meaning. Like the U here. Okay, it's a downward stroke. It curves. It comes back up, and it has a little serif there. So that's not just a line. That's a representation of something that's commonly understood as the letter U. And the word understand has a meaning that people understand. So when you write the sentence, I understand, people can parse that as a subject and a verb, and it has semantics, and it forms a sentence. And it's all there because of, these tokens have an assigned external or extrinsic meaning. On the other hand, music, tones, sounds, notes don't really have any kind of external meaning or implication. And it's similar, analogous to abstract art. Like this work, you can look at this, and it's clearly a work of art. I'm sure it's worth a lot of money, and it's in a museum somewhere. And but what is it? what does it mean? Well, you can look at it and you can see that there are rectangles of different orientation, but orthogonal, and they have different colors and a certain kind of spacing and so on. But everything I'm describing is internal to this painting. There's not necessarily any reference to anything outside of the painting. And music works the same way most of the time, that there's, all the connections and all the meaning develops internally. And so where does that come from? Well, if there's no external meaning and nothing outside of the music, then the music has to have any kind of reference or meaning, has to refer to itself, which means that you have to have repetition. So just to illustrate this, I'm going to play a random pitch sequence. Computer generated, pretty random. A lot of people would say, well, that's not music. It's just random pitches. So what if we take some random pitches and just repeat them and think about, what's going on in your head when you listen to this. So the second time this thing starts repeating, you probably recognize, oh, that something happened twice. So that thing, which was just a sequence of pitches and of indeterminate length, suddenly becomes a finite unit of a specific length and a specific set of notes. And why do we say that? Because that unit, whatever it is, got repeated. We can do that. We can take this whole operation of take random sounds, repeat them, and then repeat that whole thing. Makes new random sounds and repeat them. So now we have kind of a hierarchical 2 levels of repetition at 2 different levels. Now, it also happened that the second half actually had a very similar contour to the first half, and that was purely random, kind of by mistake, but it also gives it another kind of interesting self-reference. We can do the same thing with rhythm as we do with pitch. So here's some random rhythms. I don't even know if you would call that a rhythm. It's just kind of random timing. But when we repeat, and so here's 2 groups of 2, analogous to the last pitch example, it sounds very different. So that, bop, 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 suddenly becomes something that we can talk about, we can repeat, we can recognize it in the music. And these techniques, I mean, this is not just a psychoacoustic experiment. These things really work in composition. And I have an example from the chamber opera that I wrote. And this was when I was writing, I needed some kind of transition. And this was my first draft. So there's some pattern and some degree of repetition, but I kind of felt like I was hearing that kind of like this first example. It's just kind of one unrelated thing after another, and I was thinking about actually these sound examples on repetition, and I thought, well, what if I tried to give the audience something, a little, the listener something more to latch onto, just by repeating each measure, at least approximately. And you get this. So, whether you like that or not, or what you think about it, I thought it was a much more effective and interesting thing, just because there's a little bit of repetition and something to catch your ear and help you focus in on different aspects. Um, so let's talk about computer composition of music, and in particular deep learning. There's been a lot of efforts to learn to compose and play music with machine learning, and certainly relevant to music and technology and computer music. So a question we could ask is, does structure learning even take place in machine learning? Is this something that's learnable by machine? And the answer, at least a few years ago, was that repetition does seem to happen, but mainly on very small timescales. Um, and it was common to hear researchers produce some music with machine learning and then produce 4 bars or 8 bars and play it twice. And that in a creative field, anything is fair game, but we need to be careful when we're listening to it, because, as I just showed, you can take a purely random sequence and by repeating it, make it sound more musical, I think. And so, if the deep learning was doing nothing more than producing a random pitch sequence, then when researchers repeat it, they're basically turning that into a piece of music that has nothing to do with the machine learning. So anyway, repetition seemed to be largely missing in deep learning based music composition systems, especially at a larger time scale. And so you could ask, why is repetition hard? Well, um, I have a kind of a detailed argument here, but I think I'll try to abstract this and just say that, actually, let me just jump to the second point here. One argument is that if you want to do, when you're composing music with repetition, you really have 3 different activities. The first is do planning at some kind of structural level. I'm going to do this theme and then I'm going to repeat it. The second is you have to create some material. Here's the theme. And then the third thing is you have to actually sort of mechanically copy note for note to obtain repetition. And this all sounds, obvious for humans, but when you think about how computers and machine learning works, what machines typically learn is not a sequential algorithm like this. Like, we'll go off and do planning, then we'll do creation, and then we'll do copying. Instead, machine learning tends to take one input and produce one output in sort of one pass, and that's been incredibly effective for some things like ChatGPT, but it hasn't worked out for music very well. So I've made some claims about music and structure, and I think these are not new, but the question is, can we support these claims with some data analysis? And so a lot of what I want to talk about is, how do we use these ideas and actually go in and study music and try to learn something? And so we've been working a lot, for years now, especially on pop music, because pop music is relatively, how do I explain this? It's relatively simple in the sense that the structures tend to be rhythms tend to be 4/4. Note durations tend to be quarter notes, eighth notes, 16th notes. There tends to be a prominent melody, a separable melody, harmony, and bass. And they tend to have very clear repetition at different levels. And so all of these things, as opposed to much more freely composed classical music with development sections and there are many different forms in different kinds of music. But pop music, there are large collections that all are sort of constructed on the same principles. And so we look at pop music, and of course everyone understands that there is lots of structure in pop music, nothing new there. In music theory, people often relate structure to different features in the musical surface. So, for example, we'll say that phrases end on long notes, or phrases tend to end on tonic chords or tonic pitch. Melodic phrases tend to have an arch form. In performance terms, phrases tend to be played faster in the middle and slower at the ends. So there's, kind of a lot of rules of thumb and guides and observations that have been with us since, way before machine learning, part of music theory for, more than a century, I'd say. But you could ask the question, are these features the result of phrases, or is it perhaps that we perceive phrases when we see these features? What's the connection between these features and structure, and is there a cause and effect, and or is this stuff all just correlated? And whether there is actually structure in operation, or it's just something that everybody perceives, is kind of almost an open question. So we've been trying to separate the idea of structure from these features, like long notes and ending on a tonic. If we could somehow identify structure independently of these features, then we could actually ask, what's the connection between structure and features? And so the way that we do that is we think of music structure as a kind of data compression. So the way this works is, consider this sequence ABC, 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 ABC. Okay, so we could structure that as ABC, ABC repeated twice, or just ABC repeated 4 times. And the last of these, there are many different ways that you could represent this, but the last one is the most compact. And so we consider that to be the best description and sort of, in some sense, the true structure of this original thing. And notice that that's, we're not really relying on human opinion or perception. It's an objective measure, given a way to encode this string, what is the most compact way? And there's an answer, and that's what we call the structure. So we do something similar with music. We rewrite the music as a sequence of measures, and we use letters to represent measures, and the same letter means a similar measure. So like A, B, C, D, A, B, C, D, E, F, G, H, A, B, C, D would be an AABA form with 4 measures, 4 measures, 4 measures, 4 measures, and we can musicians would recognize this as an AABA song form, but we can write algorithms that objectively produce this kind of output, and we've also been able to identify a higher level structure where typically we end up with representations that look like AB and then X means some kind of bridge material that's unique to the song, and then maybe there's a repetition of the A phrase and then another little transition material Y and then B, that might be the chorus. And so when X and Y are 4 or more measures and they don't match other phrases, then we take them as separating what we call sections. So the sections here are A, B, and then A, and then B, B. And that might seem a little arbitrary, and it is. It works well for the data set we've been analyzing, but it's by no means the only way of getting higher level structure. All right, so now that we have a way of identifying structure from repetition, independent of music features like melody and harmony and rhythm and so on, then we can start studying the connections between structure and these other features. So, for example, this is a study of how harmony is influenced by structure. And what we have here is these different colors represent different chords, different triads. So, you know, the tonic, the second, third, fourth, fifth, and sixth. And how often do those chords occur? And this is over about 1,000 songs, so tens of thousands of measures, and all analyzed for harmonic content. And on average, across all songs, this first column is the frequency that you expect. So, for example, you know, the one chord happens with a probability of, what is that, about 0.27. A little more than a quarter of the chords are one chords. About a tenth of the chords are, what is this, yellow and red. So that's two chords and three, you know, minor second, minor, the three minor chord. Okay, so that's interesting. But what if we take structure into account? So if we look at the start of phrases, so these are the you know, small groups of repeating measures. The first beat of that first measure is going to have a one chord with a probability of about 0.65. So, you know, dramatically huge proportion, relatively speaking. So there's clearly a connection between the repetition structure and the harmonic structure. It's even stronger at the start of sections. And let's look at, let's see, I forgot to, so let's look at some other places in the music. Here we're looking at the ends of phrases within a section. So remember, phrases are small groups of measures that repeat. Sections are these groups of larger scale groups of phrases that are separated from one another by this bridge material. So if we look within these sections, the phrases are more likely to end on a 5 chord, which is a little not what I expected. It's not outside of music theory where you know, these cadence to a 5 chord is kind of a standard thing, but it was surprising to me that it's even more common than a full cadence to the tonic. On the other hand, if you look only at the section end, which is also a phrase end, but so phrase end at the end of a section, then the one chords, you know, are far more common than the 5 chord, the dominant. So, you know, that shows, you know, I think the graph, the fact that these distributions change according to structure means that that structure is somehow is real. You know, there's something really going on because we're averaging over lots and lots of data. And the fact that you have systematic differences between the phrase ends within sections and at the end of sections mean that we not only have one level of hierarchy, but we have two levels of hierarchy that are clearly happening inside the music. So in some sense, we're objectively showing that this structure, multi-level structure, is real. Okay, so it turns out we can continue doing this analysis with durations, with melody, you know, different tones of the melody, and everything we look at is statistically significant. And like there's non-random interactions between structure and harmony, structure and melody, structure and rhythm, pretty much everything we look at. And again, at least two levels of structure. We have phrases and sections, and those are appearing in our data set, which is, again, it's about 1,000 songs. They come from China. These are very popular Chinese songs, but we see very similar. These songs sound pretty Western to me, and we have some smaller Western data sets that show similar behavior. Again, these results do not depend on human judgments. The problem with human judgments is they might use the very same features of harmony, melody, and rhythm to figure out what the structure is. And so when we ask, is there a connection between structure and harmony, melody, and rhythm, the answer is, of course there is, because, you know, humans, it's just inherently correlated because of the way humans parse music. But we're kind of parsing the music based on repetition only, and not looking for, you know, tonic chords or long notes or anything like that. Okay, so another way to look for repetition is through prediction. And so we started another series of studies looking at predictive models, and particularly variable order Markov models, to see if these could leverage repetition to make predictions. And so the idea is, if you make, when your prediction is better, it's better because there must have been repetition that's helping you make that prediction. And what kind of prediction? Well, you know, you can predict you can listen to a melody, metaphorically. The computer is processing a melody sequentially from beginning to end, and at each chord or each note or each, you know, pitch, duration, the machine model is making a prediction as to what is the next thing in the music, what's the next pitch or what's the next chord, and it's going to be right or wrong, and then, you know, it makes the guess, and then you basically then tell the computer, you know, okay, here's the right answer, so what do you think comes next? And then you reveal that and say, okay, here's the true answer, what do you think comes after that? And so again, why do we do this? It's because if we can build good predictive models, then the way in which they do prediction should tell us something about music and how music is constructed. It's also a good way to measure the amount of repetition and where repetition occurs in music, because whenever something is repeated, it ought to be more predictable. To really go into detail about how this works, I should explain variable order Markov models, but it gets kind of technical and tedious. So I think I'm open to questions, but maybe I can just give you a very hand-wavy, intuitive explanation about what these are. The basic idea is really simple. Imagine if, let's talk about melody prediction. So imagine that you go to a bunch of, our data set of 1,000 melodies, and you look for every tonic note, and you say, okay, and let's say, pretend everything is in C major. So you say, okay, every time I see a C, what note comes after C? And you can just make a tally of all the counts. And if C is followed by D 20% of the time, then you say, okay, I'm going to predict D is 20%, and maybe F follows C 25% of the time. So you say, okay, I'll guess F with a weight of 25%. And so you can kind of easily construct a distribution of probabilities. Here's my prediction. I'm the weather predictor. I think there's a 25% chance of F in the next measure or the next note. And that, that gets you some amount of prediction, but then you might say, well, what about sequences? What if it goes, what if the note before the C was a B? So I go B, C, then what comes after that? So you could think about looking at short sequences of 2 notes or 3 notes or 4 notes, and that might give you a better prediction of what comes next. And that's the variable order part. So basically with variable order, you do this prediction just based on counting of all sequences of length 1 and sequences of length 2 and 3 and 4 up to some as large as you want. And then you have some way of combining, each one of these models is going to make a prediction. The longer the prefix, like in other words, the more notes you look up leading up to the next note, the better you can do if you've actually encountered that in the past. But there's a problem that, once you get up to sequences of length 5, greater than 5 notes, those sequences are almost unique, and so there's not much information to make predictions. Okay, I hope that at least gives you some intuition for what we're doing. But that's variable order Markov models, and then to measure the quality of prediction, we use cross-entropy, which is also my intuition for. I don't have a good intuitive explanation for cross-entropy. I think some of you have probably come across the equations for entropy, and sometimes called Shannon entropy. But the idea it's basically a measure of information. So the better. If you can make a prediction with complete confidence, like you're sure that the next note is going to be an F and you're 100% sure, then that F sort of contains no information. It doesn't take any more you already know what the answer is. So it's when you see the F, it doesn't tell you anything new. You already knew it. So that's entropy of 0. On the other hand, if the next note is very surprising, then it has very high entropy because it was very unexpected, and that whatever it is carries a lot of information. So entropy is a measure of information, and cross entropy is basically a way of telling you how much information is lacking in your prediction. So if your predictions are bad, then it's going to be high entropy, or high cross entropy. Okay, so let's, with that amount of intuition, which I hope helps, let's look at some actual measurements of cross entropy. And this is cross entropy in melodic phrases. And we have this graph. The horizontal axis is where are we in the phrase. So 0 is the beginning, 1 is the end. So we normalize phrase duration and average across hundreds and hundreds of phrases. And we see when we do prediction with variable order Markov models, we see the first notes have pretty high entropy. It's basically you have no idea, so it's random. This entropy works on a log scale, so you can think of, and this is log 2, so 4 would be 2 to the 4th power. So it's like you have roughly a 1 in 16 chance of guessing the right note. That's one way to look at it. But the point is that, whatever the scale and whatever you're measuring exactly, it gets more and more predictable as you move towards the end of a phrase. So that's telling us that there has to be some repetition within the phrase, because that's how variable order Markov models work, is they're looking for things, they predict things in the future that they've seen in the past. So it has to be repetition. So that's interesting, because our previous work, we weren't able to resolve, within anything within phrases, but now we can. Here is, and now we can relate this also to phrases and sections like we had before. So here's cross entropy with looking at different points in phrases. So the overall average cross entropy, and let's look at the solid orange line. This is for this graph for now. So this is saying on, our overall average cross entropy is about 1.5. So pretty low. But at the start of phrases, the cross entropy is 3. So that means, the first note in a phrase is the most unpredictable. In the first note in a section is even slightly more unpredictable. But in the middle of a phrase, the notes are very predictable. So, you can think of this as, okay, at the beginning of the phrase, I don't know what the phrase is repeating. So it could be anything, and I don't have any information. Once I get into the phrase, it's very likely to be repeating something recognizable, and so I can predict the next thing with pretty high confidence. Phrase endings are a little less predictable, as you see here. Now, what's with the orange and the blue lines? Well, the blue lines is if you train your model on all the other songs, but not on the current song that you're trying to predict. And what this is telling us is that if 999 other songs, that information is not really so useful for predicting song number 1000. So each song internally has a lot of repetition, but songs do not repeat material from other songs. So knowing lots and lots of music doesn't actually help you predict a new song. And I think that also is kind of related to the machine learning problem, that the standard thing to do in machine learning is you get a huge amount of data, big data science. You learn from 100,000 songs or 1,000,000 songs how to do prediction. And the problem with that is every time you introduce a new song, it's not predictable. It's designed to be unique and different from every other song. So all the stuff you learn, you have to kind of throw it out the window. All right, another fun thing to do with cross-entropy we thought was really interesting is how does cross-entropy evolve over the course of an entire song? So here's, again, the horizontal axis is normalized, so 0 means the very beginning, 1 means the very end. But now instead of being the end of a phrase, it's the end of a song. So, 3 minutes or so into the song. And so the question is, what happens over the course of that song with cross-entropy or predictability? And let's see, the cross-entropy now, well, it's the blue scale over on the right, and notice the scale has been flipped. So low entropy, meaning highly predictable, is up at the top, and unpredictable is down at the bottom. And so the blue curve says that songs start out being very unpredictable, they rapidly become more predictable, and then at somewhere like a quarter of the way through, they become less predictable, which is an indication that something new is happening inside the song. And think about it. Songs start with a verse and they repeat the verse, so they become more and more predictable. And then at some point, they bring in a chorus or an interlude or something different for contrast, and it becomes, that's new, so you can't predict it so well. But then you listen to that, you learn that, and from then on, the song is just more and more repetitive until, like, on average, the second half of these pop songs are highly predictable, and nothing really new is happening. There's an interesting little dip at the end here, which I guess indicates that people tend to write novel material at the end of songs for some reason. We haven't studied that in detail, but it's pretty clear in the data. Okay, so I'll move on. Now we thought, oh well, this is interesting because this is telling us we're seeing kind of a general trend that makes sense in terms of the way songs are structured. So what happens with machine learning? And so we found a bunch of machine learning models for writing music, and we generated lots and lots of machine generated songs, and we analyzed those songs using this cross entropy method. And here's the curve we got averaged over a whole bunch of songs generated with deep learning, and you see a much lower slope at the beginning, so there was no effort or understanding on the machine learning part that you need to repeat stuff immediately. And then there was no indication of any new material, a quarter of the way through or at any point that would be analogous to switching from a verse to a chorus or a chorus to a verse. So, that seems not to have been learned. And also it seems like, we don't kind of peak out at halfway and just repeat stuff that we've already learned. We seem to be introducing new material and repeating it, now and then, all the way to the end, but there's a steady upward slope. And then there's no introduction of new material at the end. So, on multiple dimensions, the deep learning doesn't seem to be mimicking the kind of surprise and predictability that we see in human songs. I think I'll skip this. Just more ways of looking at the data. So saying that machine learning doesn't work or machine learning doesn't learn much about music it's a negative result. It's not really scientific to say that, and it doesn't prove that deep learning or any other model cannot learn to how structure works in music. It's just saying that these previous works were failing on that dimension. Even though, lots of authors were claiming they had learned all this stuff about music and they were producing these great songs, when we look at the songs, they were missing a lot. And we could show that objectively. So after we, initially made these observations, people began doing some larger scale machine learning on audio as opposed to symbolic, like MIDI representations. And one of the big results of that's I think surprised a lot of people was Suno, which you may have heard of. So I'm gonna Suno is a commercial company that takes prompts like ChatGPT, but it uses them to construct music. And I'll play you something from Suno just to make sure everyone can calibrate. Here we go.
When you feel alone and the world is weighing down on you, give me a moment, please, to soothe your restless mind. I know you feel like shadows are closing in. It's hard to find the light. People can be so blind. When darkness knocks upon your door and you feel you can't take anymore, let me be the one you call. If you fall, I'll lift you high, take you up and guide you through the starry night. If you need to fall apart, I can mend a wounded heart. If you need to cry, then let it out. You're not alone. When you feel so lost and a true friend is hard to find, you're stuck on a lonely road with battles in your mind.
So we were all amazed when we heard this, and I'm still very impressed. It's really a qualitative step forward in learning and incorporating structure into music and making sort of passable human sounding pop music compositions. The audio quality is not great. I think it continues to get better and probably, conceivably will be solved. So it's not that it's great music or, solves all the problems, but still, it's a big step forward. This music is controlled by text descriptions, and part of the generation process is lyrics, which are structured, and some of the repetition in the music seems to be guided by labels in the lyrics. So the lyrics are created with explicit labels. This is a verse, this is a verse again, this is a chorus. And so there's some clear structure in the lyrics that might be helping, with this. But what can we learn from this? Well, and Udio is another comparable system. These things do have clear repetition structure. How do they do it? It's not clear. Maybe just more data. Maybe there's some inductive bias, like marking lyrics with chorus and verse. And initially, we suspected the output might be guided by some human design templates and rules. And in fact, this came out not so long after our papers talking about how to incorporate structure into machine learning. So we thought maybe they were just taking our work and turning it into an industrial size project. But I think that's probably not the case. And there's some recent work by Ruibin Yuan, who is a graduate of our music and technology master's program. He's been recreating an open source Suno-like system, and he's getting some very impressive results. He doesn't have the scale and the budget to train huge models like Suno and Udio. So his audio quality is even worse, but you can still hear it as music, and you can hear the structure, and he says that it's actually, seems to be just falling out of learning from a lot of data. So I think this is really interesting. And a colleague, Bob Sturm, suggests that as machines begin to compose more and more music than humans, music theorists and musicologists should perhaps study machine-created music artifacts just as we study human-composed music. So when we're asking, where does structure in music come from, we can ask not only about human compositions, but try to study machine compositions. So just to wrap up here, we need to understand more about music, and particularly the role of structure. I think that's a real frontier for music study. Structure can be used in AI to compose music, and we can create music without hierarchical structure. And there are great pieces of music that are structured along different lines, but at least in pop music and conventional music, results without structure are rated lower in quality. So it's measurable, it's measurably desirable. So repetition and information theory, as I've shown here, give us some objective tools, and maybe in the future, understanding more about structure can help us create new kinds of music and that humans can relate to. And there are a bunch of people who have participated in this work. So here are some names and pictures, and I'm going to stop there. We have a few minutes at least for questions.
Okay, Roger. So this is all very interesting to me because my earlier life was studying musicology, and the field that I was interested in was the same one that the great Hungarian musicologist János Bartók was studying, which was Haydn, Mozart, and Beethoven, the classical era. And Dr. Bartók, of course, the sonata form was the big thing in those days. And it's not that any composer went to school and learned from the master before them that sonata form was this, this, and this. Sonata form was not described until long after it had ceased to exist. Just by people looking at all the things, sonatas that composers had written, and then coming up with rules that seemed to describe how they were written and how they were structured. Mm-hmm. In a way, much the same way that your machine learning is doing, looking at how things were or are, and then coming up with ideas and formulas to kind of describe and recreate them. But anyway, János Bartók had a different way of describing a lot of classical music, and that was by saying that the structure was more something that he called the quatrain than it was sonata form. And the quatrain, interestingly, actually comes from literature, not from music. And it was a four-phrase structure with certain things at the end of each phrase to get back to the next phrase. And then the last thing would be an elision between the, let's say, the B phrase to go back to the A one again. And the A, B, A can be slightly different as they transverse through the whole structure. And even now, when I hear some classical compositions, I say, well, that's not sonata form, that's a quatrain. It's so interesting to me to be able to see that. I don't know how it applies to our, to your present work in this, but I did want to mention one other thing, and that is, I think one of my colleagues right now is teaching repetition in music in the School of Music as a course. So it's not a machine learning thing. I think it's just looking at different types of repetition. It could be.
Oh yeah, definitely. And there's, I'm trying to remember the author. There's a book on repetition in music, and it's certainly well known and well studied. I think our contribution is trying to find more quantitative techniques and kind of separate out, how it is that you delineate phrases, independent of musical features. So then you can really study the relationship between, choice of notes and the structure. But yeah, and also I would sort of, I think it's kind of my dream that someday machines, well, if machines are going to do something, really creative in music, I think it would be interesting to me if rather than creating another, yet another pop song, if they would do something creative in the sense of, let's say Stravinsky, who wrote a new kind of music that had never been heard before, or Charlie Parker in bebop, who kind of took, who led to a whole new world of kind of a whole new concept of jazz and how jazz was organized. There are some composers that are very creative within an existing language and a musical language, and then there are composers that really pioneer and create new kinds of new languages. And I think that if computers could understand, look at sonatas, and maybe they would not identify sonatas. Maybe they would identify quatrains, and maybe they would find other sort of patterns and structuring devices, and ultimately maybe learn the nature of these structures. What does Stravinsky have in common with Beethoven? I think at some level there is something much deeper that has to do with anticipation and surprise and repetition, that is even more fundamental than AABA structure or something like that.
One other thing that I've noticed in opera, Verdi seems to me to be almost a rhythmic composer, because there are these small rhythmic motives that are almost at the bar level rather than the phrase level that he writes in, like La Donna Mobile from Rigoletto. Dee 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 da dum, dee da 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 dum. Those rhythms, you can follow them, almost bar by bar. Of course, he knows exactly when to break out of that to make a really great aria or something. But still, it's puzzling that the organizing factor is tiny rhythmic sequences.
Yeah, and I think that's something that's very true about human perception and music construction, that we are sensitive to almost any organizing principle. So if the thing that holds the music together is a rhythm that repeats every bar, we latch onto that and we say, this is the important thing. And so that allows us to go to a new music performance where, let's say that there's no rhythm and there's no tonality, but there's some kind of timbral similarity from one section, from one thing to the next, or maybe some alteration between two classes of sounds, and we, if we're open to that as being music, then we can really enjoy the structure and anticipation that arises out of different kind of timbres or other, it could be anything. And there are some pattern recognition approaches in music that attempt to kind of look for patterns in any feature and any combination of features. It tends to explode computationally, and I mean, if you look for every possible pattern, there are so many possibilities that probably you're going to hit on multiple ones. And so it gets really hard for machines to say, okay, of all the ways I might structure this, which ones are actually predictive and likely to be, kind of the true foundation of this music. But there are some interesting developments in that direction with computers that I think are really interesting.
Well, I think the whole thing is fascinating, honestly. Are there any other questions out there?
Not necessarily a question, but I remember experimenting with like Suno and Udio recently. I'd always been skeptical of it, but I thought, I should at least try it out and see what they do. And kind of the way it's so rigidly structured, it felt to me almost as if they have a separate layer of first determining a structure, and then guiding their generative process to kind of fill in that structure. And I think that certainly works with the kind of music they're trying to come up with. Um, but I think and I've seen some papers recently that explicitly delineate these hierarchical structures into there's the larger structure of verse, chorus, verse, and then within verse there's phrase one, phrase two, phrase three, and so on. And I think to me it sounds like that's what they're doing. But I think what's more interesting to me would be, because that's a very like rigid structure, and you can only come up with so much music within that structure. So definitely what you just mentioned about, seeing if machine learning can try to come up with new music, something that's, what we haven't seen before, rather than like structures that humans have already perceived and are trying to force the machine learning to like go like follow and go into. I think that would be more interesting. But yeah.
Yeah, it seems when I listen to Udio, I don't know, it is so qualitatively different and more structured than everything before it that it almost seems too good to be true. Although, like I said, Ruben, who is actually doing hands-on research and trying to do something like Udio, is pretty convinced. I told him I thought that there were a lot of tricks and formulas and templates being used to make it sound so good. And Ruben said, he didn't think that was the case, that it seems that if you use enough data, these structures just start falling out of the data. He gave me some more details, but I'll just leave it at that. So, I think it's quite magical and very, very surprising. But like you say, it could be that the real limit of that is the thing that you're going to learn first is the most kind of normative verse, chorus, verse structure that you can imagine, because that's the thing that happens the most. But the thing that you maybe should, as an artist, that you really want to pay attention to is how composers and rock groups deviate in interesting ways. When the Beatles started playing stuff that was not in 4/4 time, it really freaked people out, but they loved it. And and I don't know, we'd probably come up with a lot of examples of innovations, but it's always, the innovation is always kind of the deviation from the norm. And so if you make really normative music, it's going to be ultimately pretty boring. And I think that's the problem with Udio that a lot of people are sensing. So maybe if you need a background that a background song for a commercial or a travel log or something that people are not going to listen to very carefully, it might be good, but if you're trying to make art, not so much.
Yeah, and kind of that was the reason why I suspected that Suno and Udio um, would almost want to like force themselves into that normative structure, because it's good for their business
Yeah,
have to have music that comes out and sounds, reasonably good, or listenable, right?
I
But
was I was at a seminar with a bunch of computer music people, and while we were there, someone entered some lyrics and some word suggestions that were kind of based on us being at this, computer music seminar in Germany, and Udio, wrote some song, and then they, being musicians, they transcribed the song and arranged it, and then recruited a bunch of us to play it live. So it was, one maybe unexplored application of Udio is or Suno is, for parties and gatherings to just make stuff that's really hilarious.
party trick, yeah.
We had a
Okay,
good time.
thank you very much, Roger, for this, and we hope to see you again soon.
Yeah, thanks for having me, and good to see everyone. See you
night.
next week.
Bye.
Bye.